Hi, everyone. It is a great pleasure and a great honor for me to introduce you, Professor Barry Clark Barish, I apologize, whom I warmly thank for accepting our invitation today. He's a very, very known scientist who actually covered in his research and in his activities a very broad spectrum of areas in high energy experimental physics, which started from his PhD in 1962 at the University of California in Berkeley in experimental energy physics. And the year after, as a research fellow, he joined Caltech in a new experimental effort on high energy physics. And later on, he would take the leadership of the high energy group in Caltech, becoming the principal investigator in 1984. Now, his career as a professor started in 1966 as assistant professor, and from there all the way to full professorship. And in particular, in 1991, he became Linde professor and emeritus in 2005. Now, for research and these results, he is known, among others, as director of the macro experiment at the Gran Sasso National Laboratory in Italy during the 80s. This was an experiment devoted to the study and investigation of cosmic radiation, the search for magnetic monopoles, and among others, also the experimental efforts that contributed later on to what became the discovery of neutrino oscillations. But surely what is best known for are his efforts in the breakthrough developments that led to the discovery of gravitational waves. He started as principal investigator in 1994 for the Laser Interferometer Gravitational Wave Observatory, so LIGO, and he led all the efforts that led to the approval by the National Science Foundation, then all the way to commissioning and even to data taking and operation. Now, the list of honors and awards that he has received is so long that I would certainly fail if I even try to mention a fraction of those. So I wouldn't even try. But certainly the most noticeable or the best known is the Nobel Prize for Physics, which he received in 2017 jointly with Rainer Weiss and Kip Thorne for decisive contributions to the LIGO detector and the observation of gravitational waves. So I would then let the mic to him, and everybody, let's enjoy this beautiful opportunity. Thank you very much.
Hello, thank you, Elisa, for a very nice introduction, and Giacomo for covering many topics that I won't have time to cover that are inherent in gravitational waves. I'm going to share my screen and then I'll start talking. Okay. And of course, I couldn't help but show this famous spot in Padova where I've been and wish I was today to give this lecture, Galileo's tribute. On the left, on my lead slide, I show what is really the theme of what I'm going to try to talk about today, which is the fact that we are seeing a merger of physics and astronomy. I note that your department was once separately physics and astronomy, and with foresight has come together because the subjects have come together. And what I'm going to try to do is introduce to you a very, very beginning of a field with tremendous potential, and that is what we call multi-messenger astronomy. Astronomy that isn't just standard astronomy, but has the physics of perhaps neutrino detections and gravitational detections, all looking at the same phenomena and understanding what the underlying science is. I show over on the left the first example that we had. I'm going to talk about it in some detail, which is on the bottom, the signal from gravitational waves from the LIGO detector, what we call a chirp signal, or a signal that shows frequency going up on the left and time on the right, and the signal increase, the little line inside that you see, increases in frequency, increases in amplitude at the time that, in this case, two neutron stars merge. What was unique about this particular event, in addition to gravitationally being able to study a new phenomenon for us, which is the merger of two neutron stars, was that the same phenomenon, this merger of two neutron stars, was observed 2 seconds later, 1.7 seconds later, by astronomers, by high energy gamma rays, what's called gamma ray bursts, on the top in the Fermi satellite. And that started a whole phenomena of that same phenomena, same place being looked at in the sky by many, many types of astronomical instruments. And I'll talk about that a little bit later. I can't help but make a conclusion, which is pretty tremendous, just from this picture here. The fact that the merger happened and we see a signal in gravity, which is the merger 1.7 seconds before we see this signal that's astronomical, means that the signal, the electromagnetic signal, traveled from 150 million light years away to us within less than 2 seconds of when it arrived in gravitational waves, which means in something like 1 part in 10 to the 15, we know that the speed of light and the speed of gravitational waves are the same. That's a pretty phenomenal conclusion made simply from this picture here. By the way, the fact that the gravitational wave signal comes a little before is a physical phenomenon, that the merger, which is happening gravitationally, of course, happens first, and then the nuclear physics that gives the emission of light happens a little bit later. It's a detail exactly how long that takes, but the 1.7 seconds is indicative of the difference between the gravitational phenomenon that happens a little before the nuclear phenomenon. So that's my first physics conclusion, and it already shows the great power of observing simultaneously a phenomenon in space that happen in this universe that happens gravitationally and electromagnetically. And I predict that's going to be a big theme of the future of our science. So I just show that pictorially here, that what we expect to do is look at the same phenomenon. When we talk about multi-messenger astronomy is the word that's used now. Multi, of course, is many, many messengers. So what we're used to is looking, and maybe in some ways, arguably the biggest advance in astronomy in the last 50 years, is the fact that astronomical phenomena, rather than just being looked at as Galileo did with light and the visible, the same phenomenon are looked at with different instruments. And that's given great power to understanding astronomical phenomenon. So I show over on the left just a set of different astronomical instruments that might look at one particular astronomical event in different frequency bands. And that's been a great contributor to the tremendous advances in astronomy in the last decades. In the center, of course, is the gravitational wave detectors. There, I show the American one, but of course, there's the Virgo detector in Italy. And on the right is the image from the large neutrino detector under the ice at the South Pole. There's also one in the Mediterranean. And in the future, and presently, we've seen what I showed on the first slide, same phenomenon, and learned a lot. I'll show you a little more with an electromagnetic and gravitational signal. And soon, I think it'll be signals from all three, which give nuclear phenomenon, gravitational phenomenon, and electromagnetic phenomenon from the same event or the same phenomenon that happens in the sky. I'm going to concentrate first, before I come to that and come to some of our events, on gravitational waves a little bit. So let me introduce you to the subject. First, it's a necessary consequence of special relativity and the fact that there's a finite speed of information travel, which I just showed you. That is, information travels at the speed, we call it the speed of light, but we now can say it's also the speed of gravity at the same time. And that's well known, and it's finite, and was the big advance, was one of the big advances over Newton's theory of gravity and Einstein's theory of gravity, that there's finite speed of information travel. So gravitational waves themselves come from a mass, the acceleration of masses, and away from that, the signal propagates in space-time as Einstein showed us, as a warpage of space-time. That is a distortion of space-time that passes through space at the speed of light and gravity and distorts it as it goes along. So it's a little different than electromagnetic phenomena. In an electromagnetic phenomenon, we know that we have connected to the travel of a light wave a photon. In gravity, or at least in classical gravity, which is Einstein's gravity, it is purely a distortion of space and time itself. And we don't know yet, we have a limit on it, we don't know yet whether there's any quantum effect or any sort of messenger that comes with it, which we call a graviton. So in classical gravity, as I talk about today, it's just a warpage of space-time that travels at the speed of light and gravity. There's many kinds of phenomenon that are accelerations of mass that could give such a phenomenon, and ones that I can't put on this picture because we don't know about them yet. And they're looked for in a technique that was mentioned just before I talked, by looking at a burst type signal, a signal that we don't know the form of, by mathematical and data analysis techniques, to see something we haven't seen. And I suspect that in time, that will be one of the richest areas, because it's almost inconceivable that everything we see in the universe, it gives electromagnetic signals so that we know all that's out there. Of course, we know black holes aren't seen in electromagnetic signals, and we've already seen those in gravitational waves. But other phenomena as well are likely to not necessarily give electromagnetic signals. So looking for them by the techniques that were mentioned are very important. I list here the general categories as we use them as scientists to develop techniques to look for, from signals from our instrument, to look for gravitational waves. The one that's been seen, and the one that I'll concentrate on, is what's called a chirp signal. It comes from the merger of two objects that are gravitationally attracting each other, like the moon around the Earth or the Earth around the sun. They're gravitationally captured, but in this case, they lose some energy as they go around by accelerations to gravitational waves, and eventually spiral in and merge into each other. Examples of that are the neutron star case, which I showed on the first slide, and I'll show a little bit later. The first discovery that we made was the merger of two black holes. And finally, there's search mechanisms that can see combinations, for example, of black holes or neutron stars, or any other objects that might happen. That has the class of signatures, which we call chirps, and we have a very precise technique to look for them. The second kind of phenomenon is a phenomenon that gives burst-like signals, and we heard a little bit about that in the introduction. Burst kind of signals might come from new phenomenon, or they might come from, for example, what are called gamma ray bursts, which is the phenomenon that I showed on the first slide, or some other type signal, and might be seen also then in neutrinos or in gamma rays. A third, and to me, very intriguing source, and if I had to bet someone what will be the next type of source we'll see in gravitational waves, I suspect it'll be this class called a class of events that give periodic signals. Notice that's different from what I talked about before, which were all some sort of signal that's transient. It just comes and it goes. A periodic signal is one that comes and it continues. And an example of that is just a spinning neutron star. To the extent that a spinning neutron star has any irregularities from being perfectly spherical, it will have quadrupole moments and it'll give a signal. So far, we haven't seen those signals, but as we become more sensitive, we might well see those signals. They have the nice advantage that they keep spinning. So once we see a signal from a periodic source, we can study it over time. We can study it better and better as our instruments become better. And so we look forward to when we can see periodic signals. Lastly, the kind of signal that might give gravitational waves are signals from the early universe. And that may be the most profound of all and represent the same kind of studies that we've seen cosmologists do with electromagnetic signals. However, they're unimpeded by all that keeps us from looking back to very early times with photons. Gravitational signals will go back to the very first instance of the Big Bang. So once we can see stochastic background signals with gravitational waves, we'll be able to study the very first instance of the Big Bang. So that's more or less all the subjects. Now I'll become kind of more specific and look a little bit at what we've seen. So first, let me talk about gravitational waves with only one semi-theoretical slide, just to satisfy ourselves. I've written down here the equation of gravitational waves with certain assumptions that I made only for the experts in the audience from general relativity. So using general relativity and with some assumptions, which I won't say that are in my slide, I can get the formula for gravitational waves, and it's the formula on the right. And the little h is what we measure when we have a gravitational wave signal. It's called the strain, and little h mu is what we actually measure as our signal. But this formula, for those of you that are advanced in physics, is very, very familiar. It's the wave equation. And so this is the wave equation, meaning we have waves, gravitational waves, just like electromagnetic waves. And they travel, as I said, at the speed of light, which is the same as the speed of gravity. And in the picture on the right, I show those. We have plane waves, only with one difference. And the difference is it has two components, just like electromagnetic waves. But those two components are at 45 degrees from each other instead of 90 degrees from each other. Why? Because gravity, quantum mechanically, is spin 2, while electromagnetic waves of electricity and photons are spin 1. So this is a consequence of basically the spin 2 nature of gravity. We haven't yet done what is done in electromagnetic waves, and that is take a observation of the gravitational waves from an event that gives us gravitational waves and separate the two components like we do with electromagnetic waves. That's to come in the future. And it's one of the possibilities that's now open to us using that now that we have 3 detectors, 2 from LIGO and 1 from Virgo. So we look forward to being able to do that. So far, our data hasn't been good enough to quite do that yet, but we can test a lot about general relativity once we can separate the two components of gravitational waves. So gravitational waves, I show here, are ripples in space-time. They travel through space at the speed of light, and then they come to us on Earth or to a satellite where we might have instruments. What do they do when they come to us? I show that in the picture on the right. If I had a circle of free masses, the little dots on this are the free masses, and the radius of the circle was L, then the circle would get distorted by the passage of gravitational waves, such that it got more elliptical, longer in the vertical direction and squeezed in the horizontal direction. And then half a wavelength later, it goes the other direction and becomes broader in the horizontal direction and shorter in the vertical direction. I'll show you why the kind of instrument we use is very sensitive to that in a second, but let's talk about the size first. This delta L happens to be extremely small. I guess that's fortunate. That's a constant of nature, maybe. The fact that gravitational waves distort space and time. The famous thing that Einstein's theory does is that gravity has to do with the distortion of space and time. Space and time, it turns out, is very stiff and it doesn't get distorted very much. So we live in a world where we barely notice it or can barely detect it. The size of it, I note in the bottom that the change in length, in the change in the radius in the picture here is that little h that I put in my formula times L, the radius, and it's a number like 10 to the minus 21 times the size of the circle. So if I have a circle of 1 meter radius, then the size of the effect would be 10 to the minus 21 meters. That's a lot of zeros and a 1 on the end. So that's why it's so hard to see gravitational waves. I draw a circle, I put free masses in it, and those masses just move a very small amount. The first experimental conclusion is that if I want to measure it, I better make the effect bigger. And we do that by making our instruments not a meter in size, but kilometer size. So the Virgo instrument, for example, in Italy is 3 kilometers. And the LIGO instruments are almost the same. They're 4 kilometers in the US. That makes the effect 10 to the minus 18, which is still a tremendously small number. And it took us years to get good enough to measure the 10 to the minus 18. I'm not going to show you all the technical details to measure a number as small as 10 to the minus 18, although it may be the most interesting part of the whole story. Instead, let me just tell you the 2 key challenges that had to be overcome in order to do that. Many of you probably have seen at some point an interferometer. That's the technique we use. The picture on the left, you'll see has a laser beam that comes in. It hits a mirror, and the beam is split in 2 and goes horizontally and vertically. And as long as there's no gravitational wave coming through, I'm showing it distorted by a gravitational wave coming through periodically. But as long as it's not, and the lengths are the same, the light will take the same amount of time to go horizontally as vertically, hit a mirror, and come back. And the 2, if they come back at the same time, we can invert one with respect to the other. They'll exactly cancel, and we'll see no light in what I draw here as our sensor. If instead one of the arms becomes slightly longer than the other, they become out of phase with each other, and we then see a signal. The accuracy we need, which is what I'm pointing to, is a small fraction of the wavelength of the laser light. In fact, to succeed, we need to see these difference in length to 1 part in 10 to the 12th of the wavelength of the light. That's a tremendously small number. And if any of you have ever used an interferometer or seen it in a laboratory, you know that you see fringes and you can measure to 1 part in 10 or 1 part in 100. Maybe the position compared to those fringes, we have to do it to 1 part in 10 to the 12th. That's the first big challenge. And it involves a tremendous amount of everything from the coatings on mirrors that we heard about a little bit earlier to a lot of very fancy techniques in interferometry. The second big challenge is to reduce the fact that the Earth vibrates so much. Our laboratory to look for gravitational waves is here on Earth. But unfortunately, the Earth moves around much more. We don't feel it so much ourselves, but much more than we can tolerate to measure gravitational waves. And so we need to basically float the instrument above the Earth and isolate it from the motions of the Earth. And that's also a very big challenge. Again, if I put a number to it, at the low frequencies where we've seen black holes, we have to reduce the vibrations of the Earth to, again, 1 part in 10 to the 12. That's a tremendously small number. Those are the two challenges that took us so long experimentally to be able to develop instruments that could detect gravitational waves. Now we have instruments in both the US and in Italy that can see gravitational waves. I'll concentrate on the ones in the US as an example, but remember that the third one is very similar with some slight differences in technology. In the US, we wanted to put our two instruments far apart from each other. They're 3,002 kilometers apart. They're, for political reasons, were picked to be in Hanford, Washington, and Livingston, Louisiana, even though they were proposed by our collaboration from Caltech and MIT to be in California and Southern Maine near our institutions. But they gave us money and put it in Hanford and Livingston. 3,000 kilometer separation is at the speed of light 10 milliseconds, which means the maximum difference between when the arrival time can happen in Hanford, Washington and Livingston, Louisiana is 10 milliseconds. It can be 10 milliseconds earlier or later in each of these observatories, but within the plus or minus 10 milliseconds, the arrival is at the same time. We use that to guarantee that we see a signal that's real. And we look at the times when they're not within 10 milliseconds of each other to see any possibility of seeing signals that aren't real that would fool us. And so that's how we measure our accidentals in the instrument. This is a picture of our two instruments in the US. One in Hanford, Washington, that's a very desert-like area, but high desert, high altitude, a couple thousand meters in height. And it's very dry, as you can see, with mountains in the background, but very flat. The one on the right is Livingston, Louisiana, and it's in a much wetter and more tropical area, and it's in a pine wood forest where the pine woods are commercial and used to make paper afterwards. They look very different physically here, but the instruments are absolutely identical. And in fact, we work very hard to make sure that if we make any change in one of the instruments, we do exactly the same change to the other instrument within hours. And so the two instruments are kept exactly the same, unless there's something we haven't managed to do yet in one compared to the other. So for most of the running, they are identical. In recent running, we haven't made a few changes in Washington that we made in Louisiana, so it's not quite as sensitive, but that's just because we haven't done them yet. This is the first signal we ever saw for gravitational waves, the discovery itself. And let me just show you, because you can see it physically first. Rare in physics, this is essentially raw data. This hasn't gone through a lot of computer processing. The only thing that's been done is that it's been the frequencies outside of our frequency band have been removed. So frequencies that are within the bands that we can measure are here. Otherwise, they've been removed. And otherwise, this is just the raw data. The top frame is time, about 0.2 of a second going to the right. And you'll notice on the left, the scale is the 10 to the minus 21 that I showed before. And you can see the signals go up and down and get almost as big as 1 10 to the minus 21, just what I showed. And as you go to the right for 0.2 of a second, they get narrower and they get bigger. That's the so-called chirp signal. a signal coming in for gravitational waves and getting narrower and bigger. You can see that they essentially look identical except for the color for the top frame and the second frame. One is in Hanford, Washington, the second one in Livingston, Louisiana. And in the third one on the bottom, we just put one on top of the other, sliding it slightly. I think it's 6.7 milliseconds because the arrival time is different and they land on top of each other. That is the signal for gravitational waves. I like this, which is a figure from our discovery paper, a little bit better, but let me show you why. The top frame is the same two signals, the signal from Hanford, Washington, the signal from Livingston, Louisiana, and the second frame is the calculation using Einstein's theory of what would happen if it was two merging black holes at the masses that best fit our data. And you see that it has the same shape without the wiggles that come from experimental uncertainties or noise in our instrument. Experimentally, and we've done no other analysis, we then subtract one from another, and that's shown in the third frame. And as an experimentalist, that's a wonderful test of whether you have any effects you haven't paid any attention to or noticed. And instead, all we see is just random up and down. That's the uncertainty or noise in the instrument itself. And so even in this very simple picture, how well we agree with Einstein's equations is what gave us confidence, seeing it in two instruments, seeing it very cleanly compared to any background, and fitting so beautifully Einstein's equations for the merger of two black holes gave us the confidence on one observation, one event, that we'd made the discovery of gravitational waves. That wave, it turns out, has a huge amount of information. This is the formula, first order term in the formula for the shape that I drew in the last slide. There's a second term. In this term, this is called the chirp formula. In this term, we're able to determine, for example, the mass ratios, the spins of the two objects. The redshift is directly measured. The amplitude tells you how far away it is, looking at the luminosity. And there's a second order term that tells you more about the spins and the precession and so forth. So to the accuracy that you measure this waveform, it has a huge amount of information. So it isn't so much that you need many, many events to get information. You need a lot of accuracy on a single event, a good signal to noise on a single event. And from that, we tell the sky location, the distance, the binary orientation, and time delays, and so forth and so on. The region that we're sensitive to on the Earth's surface has to do with what I showed you earlier, getting rid of the seismic background. What I show here is all the different backgrounds are the primary ones that limit us on the Earth's surface to making an interferometer sensitive to gravitational waves. The shaded area is where we're sensitive, and this is just pictorial. We're limited by seismic noise, that's the shaking of the Earth at the lowest frequencies, but you'll notice how steep it is. It drops very, very fast because it drops to the fourth power of the frequency and is really only a problem at the very low frequencies. At the highest frequencies, we're limited by what's called shot noise. That's the name. What it is really the photostatistics, how many photons you have in your interferometer. And so in our case, we have a very, very powerful laser, and we have many tricks in order to keep the light in the interferometer for a long time and have very good photostatistics, and that affects the right side. As we increase the frequency, we sample it faster and faster, and the photostatistics gets less. In between, we're limited by the word thermal. We're limited by some sort of KT noise. In this case, I wrote it as suspension thermal. It's what was mentioned early before I talked. For example, the surfaces, coatings on the mirrors themselves, or the wires that the mirrors hang from to make them suspended. But those are the backgrounds, and that's what we do experimentally. I'm not going to go through experimental details, but rather just to give you a sense. Notice that we cover the same, it has nothing to do with audio, but on the Earth's surface, we cover the same band as the audio, tens of hertz to thousands of hertz or 10,000 hertz, just like audio signals. So that's the band we're in, even though it's not audio signals themselves. This is a plot that I like because it's a progression for our first version of LIGO, from first turning it on to making it better and better and better until we got to the design. This started in about the year 2000 until 2005 on the first version. And the different colors represent probably half a year or so in between where we would take data. It would be more sensitive, of course, is going down, like in this plot. The little line that's shown here is the calculated best sensitivity. And we kept improving by knowing what limited us each time we turned off until we got to the final design sensitivity, pretty much. And then we did a complete rebuild to what we call advanced LIGO, which was a more sensitive detector when we were able to make the detections that I show. That's all I'll show technically about the apparatus. What I want to show next is just the number of events we have and then some interesting events. So what we have is the very first run we call observational run. We're observers like astronomers. Number one, that was the first discovery of gravitational waves, and two more events that we saw during the first run. That run took a year, or almost a year, 6 months, and we saw a couple events. We then turned off for maybe 6 months, I don't remember exactly, and we made some improvements in the apparatus. And you'll see in the second run, we had maybe 10 or 11 events by the end. We had twice as many events in that running. In the third run, which was for a year, ended by a little early here by the pandemic, which came last spring, we had a much higher rate, and we now have something like 67 events that I included here. It's slightly different than that, but 67 events, 3 from the first run, 8 from the second, 56 from the third. And with the improvements that we're putting into the detectors now, we expect to have, we had 56 events in 1 year. So 1 event a week, and it'll be about 1 event a day next. So this keeps improving because for the gravitational wave detectors, we're limited by physical phenomena, by noise, by how well the apparatus works, and so forth and so on. We're not limited by physics. So in contrast to my previous field, particle physics, where the Higgs was discovered at CERN in 2011, it's been hard to go very far past the discovery of the Higgs because the Higgs is a very small effect on a large physics background. A physics background, you can understand it better, subtract better, but you can't get rid of it. We don't have a physics background. We have noise or shaking of the earth or electronic issues. So as we improve the technology, we get better and better and we see more events. We have another nice feature for gravitational waves, and that is if we improve our sensitivity a factor of 2, we increase the rate of events a factor of 2 cubed because we see a factor of 2 further out into the universe. So that means that the future of this is limited only by our ability to make better and better detectors. And that's why we're so confident that this will open up into a very big field of a big observational field where we can do, for example, multi-messenger astronomy. And we're in the very early phases of that at present. Over this run that we had for a year, we measured many of like what we saw in the first event, mergers of 2 black holes. These pictures here are each of these different mergers, 2 objects coming together and making a heavier one. And you can see They have different masses and so forth. We're studying those now. I'm not going to talk about them. I don't have time. We're studying those now to try to understand the distributions, how far away they are, what the difference, what the masses are, what we know about the spins, statistically, like you might do in particle physics when you got a number of events, in order to try to understand what was the origin of these black holes. How did they originate? Did they originate just from the stellar collapse of stars? Did they originate somehow dynamically to get these very heavy ones? Or maybe they were primordial and made in the Big Bang itself. By studying the properties of many events in the very way we tend to do physics, we can do that. We don't have sharp conclusions on that yet, and I don't have time, so I'm not going to show you those distributions. But that's a big part of what we're doing. Instead, I'll show you what I call exceptional events. So most of them look like this. They look like the pictures on the left. These are a set of these events. They may ring for a different amount of time. That's the different parameters of what the masses are, how far away they are, and so forth. On the bottom right is an event that we saw in 2017, 1 year after the discovery of the black holes, that was quite different. These events that we've seen, that I showed in the very first event and all the others, we see a signal as long as typically tenths of a second. Maybe it's 2/10 of a second, maybe it's 8/10 of a second. It depends on the masses of the events. We saw an event in 2017 that was not just tens of seconds, but a minute maybe or more in the apparatus. And so here's 10 seconds, 20, 30, 40 in an event that looked like that. That's immediately different. The reason it's in the apparatus so long, the reason the signal is so long, indicates that the masses are much lighter. Once we studied this, we saw that it's 2 neutron stars, and that was the picture that I showed on my introductory slide. And that was what enabled us to look and see that there's also electromagnetic signals within 2 seconds of that. What do we have to do this multi-messenger astronomy? And I'm just going to point out the challenge. We have to basically take LIGO and Virgo together, analyze the data very quickly, see not only that we saw an event, but where it happened in the sky, make sure we have some confidence of what we've done, and then announce it to astronomers so they can look. And we'd better be pretty confident because they may have to turn their instrument off of what they're doing or point it in the sky where we are. That means within a few minutes, we have to analyze the event and tell the astronomers in a message what we have, and hopefully not have to pull it back too often. We have techniques to do that fairly well. With about 80% of the time, we basically are correct are maybe not as accurate, but correct in alerting astronomers and where to look in the sky. And we did that for these 80 events that I showed. There are no reported electromagnetic observations from these black hole mergers, none. So we don't have any published data that saw anything. We don't expect anything electromagnetic from the black hole mergers, but we didn't see anything. In contrast, that neutron star event immediately we did see. Now, experimentally, to point in the sky is a challenge. We have to do that by having detectors that are spread around the world in different places. We presently have 2 in the US and Virgo in Italy, but there's also a detector being commissioned in the Kamioka mine in Japan. And we're building a 3rd LIGO instrument in India, all of which will be working within about 4 or 5 years. Presently, our ability to see around the world where something comes from is shown in the upper left picture here. And if we're lucky, we're in a region where it's good, but we need better coverage to do better. Once we have all 5 detectors, which is the mid-2020s, we'll be able to tell pretty accurately anywhere in the sky, which is the lower right-hand corner, by the mid-2020s. This was a picture of when Virgo joined us and we were able to see events with 3 detectors instead of 2. These big stripes are what we were able to do with LIGO's 2 detectors themselves on events before Virgo was finished. And then once Virgo turned on, we were able to see in the sky to tens of square degrees where we are, and that's good enough for astronomers. This happened in August 2017, and soon after that, and all the events, as I said, have no counterpart. But soon after we saw this event that I showed on my lead slide, we saw it in all 3 detectors, as is shown here. That allowed us to point in the sky to tell where it is in the sky. And that's shown in this picture here, with LIGO and Virgo actually better than was seen in the Fermi telescope. Other observational techniques determined actually which galaxy it was from, which has helped us tell exactly how far away it was that this neutron star event happened. And from all that information, we've been able to do this science with gravitational waves from the merger of the 2 neutron stars. The most interesting effect, maybe, is the following, that the phenomenon of what happens when 2 neutron stars merge had many theoretical interpretations, but a popular one was called a kilonova. You've heard of a supernova. That's the collapse of a star after it burns up all its fuel. A kilonova is a model for the merger, nuclear physics-wise, of 2 colliding neutron stars. And that can be tested if you had data on a neutron star merger at all different frequencies or wavelengths. And so that was done. Once we could point to this event, the neutron star merger itself, we saw the gamma ray bursts, I showed you that, but we also could see other astronomical signals all the way till you see X-rays or radio. And signals were seen in all those different frequencies over a period of time. And that fit a particular model called a kilonova. That model may or may not be definitively right because this is only one event, and usually we need more observations to be definitive, but it's tempting to look at that and see what you can conclude from that. And this is just a picture of the different colors that come from the neutron star as observed in the electromagnetic information and compared with the lines, which are the calculations for the different colors that come from the calculations of a kilonova. From that, we're able to make a quite interesting conclusion. An embarrassment for physicists for years is, as we try to, of course, explain all physical phenomena, is that we've never had a good explanation for how the heavy elements got into the Earth. The Earth was created. We mine in the Earth and we find heavy elements. Some of them were very desirable, like gold and platinum. But how did they get there when the Earth was formed? Usually, we blame it, or we think it came from supernova. We know that most of the universe is made of hydrogen and helium. The way we make heavier elements is in the fusion burning of a star. But the fusion process only works up to about iron. It doesn't make heavier elements. You can have enhancements that may make a few of them, and there's one that nuclear physicists use called the R process. But it was always hard to reconcile that with the number with the amount, let's say, of gold and platinum in the Earth. It may be, and I say maybe because it's only one event, that it's describable by the fact that we saw it in the collision of neutron stars. And in the collision of neutron stars, I may have missed a slide. In the collision of neutron stars, you can calculate that you made much, much more gold And maybe that's the reason. I may have the slide out of order. If not, I'll just say it. Now what we're doing is looking at the 100 events or so that we have and looking at what we call exceptional events. And I'll end by talking just a couple minutes about those. This is an example. So we talked about two kinds of objects in the sky, neutron stars and black holes. Neutron stars come about from the collapse of a star after it's lost all its fuel. And sometimes it ends up as a neutron star. We study those astronomically. They are pulsars and give electromagnetic signals. And they tend to be about 1.4 times the mass of our sun with some spread. They're well known and studied astronomically, and the spread looks like this. We see events that are 5 sigma away from that, a couple of them. What they are, we're not sure yet. The next place where there's mass, a possible object that we know, is black holes. But these objects are too light to be black holes because you need to have a certain amount of mass to have enough gravity so that you're black or you're a black hole. And we think that's about 3 solar masses, not for an event that's a merger, but for the objects themselves. So we've studied those events, and we have the properties of these few events that we're looking at and have written papers on them. And it may be that they're new phenomena, or it may be that our accuracy isn't what we think it is, or it may be that what we think is the lowest mass where you can make a black hole or the highest mass that can be a neutron star are different than what we presently theoretically believe. This is the heaviest event ever seen, and it's way beyond anything anybody believed was possible. This is 150 times the mass of our sun. You'll notice the signal looks a little different than the signal that I showed earlier. It doesn't have that chirp-like signal. And in fact, to see it, you use this burst kind of analysis that was described before I talked. But you'll notice that it looks the same, except for the size, in Hanford, in Livingston, and Virgo. The difference in the size just reflects the difference in the sensitivity of the 3 instruments, but we see it in all 3 instruments. And the mass is very, very heavy. So we're studying now to see what that is. It could be that it's just a very, very heavy black hole merger, which means we're only seeing this part of this spectrum, or maybe it's something else. So there's alternate possibilities that it could be new science. So right now, what we're doing presently is looking at such exceptional events. This is the different interpretations of that so-called black hole merger, very heavy black hole merger. We've only had one report of a possible electromagnetic signal from that event. And this is that event, but it hasn't been seen in other detectors. So we're not sure that there is a signal. So whether it's really a black hole that's very heavy, it wouldn't give an electromagnetic signal. Whether this report is right or isn't right, we're not sure, but that's what we're studying now. Now let me reflect just before I close on the future. We know how to make LIGO and Virgo and Kagra in Japan more sensitive, and we're doing that. And over the next 5 years to 10 years, you'll see us incrementally get better, just as I pointed out, and the event rate will get better. We know also that we can make much better instruments and be much, much more sensitive. I show here the European proposal for a next generation detector. This would be in the 2030s when it's built. We have a different concept in the US, but it doesn't matter for the purpose that I'm talking today. I'll show the European and in fact the Italian one. It has features that make it better, and I've listed those. The first is to make it quieter, get it away from all the things that limit us on the Earth's surface. So it's deep underground. There's 2 sites in Europe, one of them actually in Sardinia. So it may be built in Sardinia. The other is in Holland. Make it bigger. So rather than 3 and 4 kilometer arms, 10 kilometer arms. It can be a triangle, which allows you to have the beams going around clockwise and counterclockwise, which gets rid of a lot of problems and enhances the measurement capabilities by making it a triangle. You can measure, for example, something I mentioned earlier, the polarization of the gravitational waves that way. A big step is to make it more quiet from thermal noise, just room temperature noise that we presently have in our instruments. And that's to cool it to cryogenic temperatures. And I mentioned that here. And optically, we can make the instrument itself specialized so it's more sensitive, but concentrates, say, on the low frequencies or the high frequencies. And so that kind of instrument is, again, the way it'll go in the future. What that'll enable, I show here, actually, I picked a plot that's our American version of a future detector, but it doesn't matter. Presently, we are doing this, that's advanced, we're here. This is the limit of what we're doing in an advanced LIGO. Improvements we'll do over the next decade will bring us down to here. This is the sensitivity. What was 10 to the minus 21 is getting down to 10 to the minus 23. With its next generation detectors, like the Einstein telescope, or what we call the Cosmic Explorer in the US, it'll go down to 10 to the minus 24, 10 to the minus 25. What does that do for you? It makes us be able, on this plot here, to look out toward the edge of the universe. This is the redshift. So for the black holes, we get out to a region here of redshifts of 100, which is the very early universe. So we, in the next generation, will be able to start doing cosmology, or early universe physics, with neutrinos in the 2030s. And with that, and which is an optimistic note, I'll end with a nice picture of Galileo. Thank you.
Okay, thank you very much, Professor Barish, for this very beautiful colloquium. It was very clear and very instructive at the same time. So really, sincerely, thank you very much for that. Now, I would like to invite everyone to share questions with us. You can use a Q&A button, so questions and answers dialog box. This is the way you can communicate with us, and you can type your question. And then I'm gonna read your questions, and Professor Barish will answer. So while the attendees are typing questions, I can already share you one, which was sent while you were talking about the Einstein telescope. So I think it refers to that. The question is in Italian, but I will translate that. And it is, the new technology that you are talking about, can it be more precise in measuring the distance of astrophysical objects, or at least can it be more precise in comparison to traditional astronomical observations?
It is very easy to tell distance, because distance is directly proportional to the amplitude that we measure in gravitational waves. So it has less difficulties, which is more indirect, how you measure a distance electromagnetically. So as we improve, basically linearly, as we improve our ability to make larger signals, we improve our ability to measure the distance. One obvious gain that we'll make when we do that is to be able to study what is presently a problem for astronomers, the Hubble constant. That's the expansion constant of the universe. And it's done 2 different ways by astronomers. And so far, those 2 ways have different results. They call it a tension instead of a disagreement, astronomers. It's completely independent to do that with gravitational waves. and depends on our ability to tell where it happened, a distance, when we detect a signal like a black hole merger, like a neutron star merger. And in the future, if they don't resolve it astronomically, I think within a decade or so, we can measure well enough the Hubble constant that we can be independently do that. So I've answered you in two ways. One is yes, we'll keep getting better and better. And in fact, there's a direct consequence of that. For example, in the finite future, which is the ability to measure the Hubble constant.
Okay, I would like to encourage all attendees to share questions with us, and in particular students. Please take the opportunity to ask all what you always wanted to know about gravitational waves. This is definitely a unique opportunity that you shouldn't miss. So meanwhile, there is another question. What do you expect to observe from redshift 100 with gravitational wave detectors?
Oh, well, let's reflect a little bit. I think the most one of the most important questions in physics and astronomy is what happened in the early universe. We all wonder, what was the Big Bang all about? We also have a phenomenon in the early universe, which we only indirectly can relate to and not explain, called inflation, that the expansion of the universe was very fast for a short time in the early universe. And that all comes indirectly right now, mostly from the fact that we observe low energy photons in what we call the cosmic microwave background signal. That measures basically the leftover signal of photons at low energy coming from the very early universe. The problem with it, and everything we know and have now, is that the signal only goes back to 300,000 years after the Big Bang. So we have to extrapolate to anything earlier than that. And that's the conclusions that I've drawn for you. If we can measure neutrinos, that's very hard, or gravitational waves going back earlier than 300,000 years, doing the one that I talked about with black holes is just one aspect of that, then we actually open up the possibility of seeing the phenomenon in the early universe to the very earliest times. There's two ways that we do that. One is to measure very large redshift for the phenomenon that we've seen, and that can go back to fairly early times for a dynamical phenomenon. And the second is to actually look for the equivalent of the cosmic microwave background signal, but for gravitational waves. We do that in LIGO, but we haven't seen them. And that's to look for a stochastic background that would come from signals in the early universe. Probably we should have detectors at lower frequency to do that right, because they're at low frequency. And it's very hard to do at the kind of frequencies we have in LIGO. And it may be that the space experiments, which will be done in the 2030s, called LISA, will be able to do that. Or it might be that we can do it in LIGO. It's one of the physics goals that we have, and we look, but I don't know that we're sensitive enough. But as the detectors get more sensitive for dynamical phenomenon like the merger of black holes, we can go to earlier times, cosmological times, and understand maybe whether they're primordial or whether they're dynamical. And we can hopefully someday see stochastic signals that really look at the very first instance of the Big Bang.
Okay, then we have another question. Are there any predictions for gravitational waves from supernovae?
That's a very good question and a very difficult topic. The problem is that gravitational waves come from, I didn't mention that, but electromagnetic waves come about, we all know the Hertz experiment that made electromagnetic waves. It comes from having a dipole, a plus charge, two charges oscillating with each other. And then that made, like Hertz did to make them. Einstein showed in 1918 that gravitational waves are produced by a quadrupole moment. So basically the production of gravitational waves comes from whether there's a quadrupole moment or not. The question then is, when a star collapses, the star collapses when it's burned up all its fuel, its nuclear fuel in the fusion process, which had an outward force, and that is no longer sufficient to balance the attraction of gravity, and it collapses by gravity into an object at the center. And that object might be a neutron star or whatever. The question is, when it collapses, how symmetrical is it and how non-symmetrical is it? And we don't know. There's models, but we don't know. It's very difficult to calculate. We know that it isn't perfectly symmetrical because the final objects in a supernova tend to be, say, a neutron star that travels at a few hundred kilometers a second. They would stand still if it was totally symmetrical. So we expect that there's a quadrupole moment, but we don't know how large. From the best estimates now, the present day detectors can only see a supernova out to past, we can see our whole galaxy, but not much beyond that. There's one supernova per year if we could see as far as the Virgo cluster. So if detectors got good enough to see to the Virgo cluster, then we could see one a year and then be able to study whether or not it has a gravitational wave or a quadrupole moment. But right now it's a rate problem. We haven't seen any, and we haven't seen any since Galileo's time in our own galaxy anyway. So.
Another question is, can gravitational waves test the quantum nature of gravity? And if yes, how?
Great. That's a very good question. In my mind, the biggest embarrassment being a physicist is that we have two wonderful theories of physics. We have Einstein's theory of general relativity and all its successes, some of which I talked about today. And we also have a second theory of physics based on quantum mechanics, quantum field theory, that does particle physics extremely well. And in fact, so well that almost everything that happens in a big machine like the CERN collider is predictable using quantum field theory. Yet, there should be one theory of physics. We have one theory of physics we use at long distances, Einstein's, and when we use at short distances, quantum field theory. There must be something in between. Theorists, of course, have known this and worked on quantum gravity for decades, but we don't have a successful theory of quantum gravity. Maybe we'll get one. They work hard on it. My belief is that we need some sort of experimental clues to form a theory that's new, that brings together Einstein's theory and quantum field theory, if you want, into some sort of quantum gravity. And there's two potential places that might happen. Maybe from information from the early universe, if we could do the kind of thing I talked about earlier. But I think the second candidate and the place is to find some place in nature where you have to satisfy both quantum mechanics and general relativity at the same time. Then we can understand maybe how to bring it all together. And the place where that, I don't know how to do this, I'm just going to tell you where. I think the place that's a candidate for doing that is black holes. So the fact that we see black holes and see all the general relativistic features, and the fact that we're getting better and better at it, for example, with the Event Horizon Telescope, not with just gravitational signals, but studying black holes astronomically, astrophysically, and with gravitational waves and maybe with neutrinos. Secondly, black holes have to be able to conserve quantum numbers and all the things that we have, angular momentum, all the things that we have in quantum physics. So if we can somehow turn black holes into a laboratory where we can study, I don't know how to do this, I'm just telling you, where we can where we can study both quantum effects and relativistic effects in the same phenomenon. Maybe we can get the experimental clues that'll point us toward how to bring us to one theory of physics. And so finding the quantum nature of gravity is a really important, maybe the most important problem that we have in physics. And my dream is that maybe we can do it with black hole. Maybe the place to do that is in black holes. And I don't know how to do it.
Professor Barish, how much time can we still take from you? Because we have many, many questions.
You can keep going. It's okay.
Okay, then I will keep selecting a few. Thanks, everyone. I will then try to pass the questions afterwards if we don't manage to process them all live now.
Okay. Okay.
There is someone asking you some more information regarding the periodic signals which you have mentioned at the beginning. Is there anything that you can say about predictions on amplitude and
yeah. So I'll say the problem we have. I think that first, I think the periodic signals, once we measure them, are fantastic because we can keep measuring. So if we find one, we can keep measuring it because it's there. It's not like the black holes that collide and they're gone. And as we make better instruments, we can keep studying the same phenomenon. What can we learn from it? We can start learning about the neutron star equation of state, a nuclear physics phenomenon, to describe what a neutron star is made of, how it works together in this compact environment. We really don't understand nuclear physics in a compact nuclear environment. This is tremendously compact. So it's a whole new area of nuclear physics. We try to do that a little bit on heavy ion colliders, but the neutron stars can be a laboratory of their own. So now let me say what the problem is, why it's hard. Yes, neutron stars, can't possibly be totally spherically symmetrical. So they're going to give gravitational wave signals. The problem is we're looking at a place where it's less and less likely. And that is in order to see a signal from a neutron star, we have to track it and watch it go around and around and around and measure a signal over a long period of time to identify it. And then see if we can do that. We can do that from the very known neutron stars. But the very well-known neutron stars, Cygnus X3, very known neutron stars, have been around a long time. And being around a long time, they give a very constant frequency electromagnetic radio signal, which is how they were seen. So all the neutron stars that we know, most of them, are very old. But getting very old, they're very, very symmetrical. So the ones that we look for that are easy to see are likely to be very, very, have very tiny asymmetries. I think the last time I looked at the numbers, our limit using some of these known sources on how big a mountain a neutron star might have. A neutron star is probably 20 kilometers across, something like that, is less than or similar to maybe a millimeter. So we know there's no mountains on them bigger than maybe a millimeter, but these are old neutron stars. So what you want to do is look at young neutron stars. We know that the young neutron stars, the reason they're not found by radio telescopes is that they haven't settled down yet. They do have quadrupole moments. They also have different frequencies that they emit. So they haven't come down to a single frequency yet. So we should look for young neutron stars. They're not identified, unfortunately, in radio telescopes, or not many. Anyone that is barely younger or is changing frequency, we try to look for. But instead, we have to do our own all-sky search. That means we have to follow every place in the sky and follow the astronomical coordinates as it goes around the ephemeris and so forth. And that's covering the whole sky is a computing problem that is way, 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 way beyond anything we can do with computers that are owned by LIGO and Virgo. So what we've done to make it a little bit better is create something that you can go find if you go onto the web called Einstein at Home. So look for Einstein at Home on the web. And what we've done to give us a little more computing power is that we use background cycles on people's home computers to help us look for signals from neutron stars that are younger or haven't been seen by doing an all sky search. Every point in the sky where we do that, we have 3 home computers somewhere that are looking at the same piece of the sky and the same data, and we compare that. With that, we've been able to do maybe, we still are limited by computing power, but we've been able to do maybe 10 times better than we can do with our own computers. And so far, we don't have any evidence of seeing something. My belief is that we will. It's just a question of us getting enough time and sophistication and better computing and so forth. And we'll be able to do that, or having a target one that's seen, that's changing its frequency from radio telescopes or something. But once we identify one and have it, it's such a great laboratory to study. I think it'll be a wonderful next phase for gravitational wave science.
Okay, I will pass you other 2 last questions. We have more, I have to admit. We will address them offline. I selected 2. So one is, if the binary black hole event, gravitational wave 190521, was indeed associated with an electromagnetic counterpart, what would that imply?
That's a good question. And I don't know the answer. So first, we don't really know what the event is. When we talk about black holes, it's hard to understand how black holes come in 2 types: the ones that are at the center of our galaxy, which won this year's Nobel Prize, which are huge, heavy things, and black holes that are stellar, that we think came from the collapse of stars originally, that we usually think of as what we've seen. And those are the 2 physical kind of black holes that we know of. Black holes are a mathematical phenomenon. So a black hole is when you get mass concentrated enough so that even light can't escape. So when the density gets heavy enough that it can't escape, so it can come from different kinds of phenomena. There's a gap bigger than 100 solar masses and lighter than what it takes to make the huge black holes at the center of our galaxy, which has to do with mergers of galaxies and so forth, that we don't know how to make them. So it's always been a place where it's expected that there's no black holes. If this is really a black hole that's in that region, that gives us some clue that maybe that's not completely true. What the electromagnetic signal might do, I don't know, because black holes themselves don't give them. That has not been confirmed by any other electromagnetic instrument, so it might be wrong. I don't know. It's not confirmed. There's a lot of telescopes and electromagnetic instruments around, so it remains somewhat controversial. But for completeness, it's published, and it's the only published result that I know of on any of our black hole observations from any electromagnetic observation, and I'm not sure that it's right or what it means if it's there.
Okay, and then the last question is, what about future perspectives to discover the graviton? What do you think about it?
Yeah. Well, the first thing is we look for it. So, and that maybe I'll just concentrate on that rather than vaguely. So I showed you on the first slide, and I emphasized elsewhere, that we can take Einstein's equations and very accurately calculate these waveforms. It's a very difficult problem, by the way. We have to do it for LIGO and Virgo. We have to use computers to calculate Einstein's equations. It's called numerical relativity. It's a whole field in itself, and it can be very, very difficult calculations. That put aside, we know how to calculate these waveforms very, very accurately. And that's how we can tell all the details of these collisions, even the spins and so forth, and the masses and how far away it is. And how might those shapes get altered if there was a graviton? They would get altered by the fact that if you put a graviton in, it's going to have some finite mass. If I put into Einstein's equations a finite mass, I put in physics a dispersion term. So if I added a dispersion term to the equations that I calculate in Einstein's case, it'll alter those shapes just a little bit, but in a very known way. And we search for that. And we have the best mass limit, I think it's 10 to the minus 25 eV squared on the mass of a graviton. If it gives, for example, if it acts in the way that it's got a tiny mass. So that's one way to search, and it's the most direct way now, is what we do, and trying to see some deviations, slight deviations that would match a dispersion term in the waveforms that we measure in these events that I've shown.
Okay, thank you very much for this beautiful lecture, Professor Barish. I will collect the remaining answers and pass them to you.
Okay. Okay. Thank you for being patient and listening. And I enjoy my visit to Padua. I only wish I were there.
We hopefully will be able to invite you personally here soon.
Hopefully we'll be through with this pandemic and I can come back.
Thank you very much for being with us today.
Okay, bye everyone.
Gianpaolo, do you want to say a few words?
No, I guess so. I thank again Professor Barish for the beautiful talk and also for his time he spent to answer the questions. And also, I guess all the students appreciated, not only the students, also a lot of us. And we hope really to see you back in Padua in this beautiful lecture hall. So it will be a completely different experience for you and also for the audience.
I look forward to it.
Okay. Thank you again, Professor Barish.
Okay. Bye. Bye. Bye, everyone.
Bye-bye.
Bye-bye.